Hey, good morning, Uncle George and TA. This is Tony out in California for Distributed Systems. I've had to redo both assignments. I guess I realized in hindsight it wasn't quite what we wanted. I was kind of doing more what I wanted rather than the literal assignment. So, assignment asked specifically for sleep and sum only. Instead, I was kind of ripping through some Amazon data and building a graph and did involve some summing, but it was kind of different. So here we go, redoing it. Should be back on track after this. My project proposal looks good, and that will be in on time. All that will be remaining is to finish the redo of homework 2, and that should be done by Friday. So again, I'm working in Ubuntu 14.04. Real happy, it's real stable. I like it. So basically we got a flat file with vertices in ascending task order, assuming the computer, it puts stuff on the stack as it needs it, kind of like that. So this is assuming some kind of order here in the flat file. And there's a couple math functions we could do. We could take the cumulative sum of vertices, we could take the cumulative sum of edges. But all I'm saying is, like, vertex 0 is sleep, has no dependencies, right? Vertex 1 sleep, no dependencies or edges. Vertex 2 says add up two numbers, get two numbers somewhere. What are those two numbers? I'm just going to say preceding two vertices, so 0 and 1, that would be the edges. Vertex 3 sum, three numbers now, so 0, 1, 2, preceding three vertices. On and on we go. So that's the way the flat file is set up. I think for the math function we'll just do the cumulative sum of vertices and leave the edges alone, but just wanted to explain where the edges came from. Again, the edges are dependencies. You need these numbers to exist somewhere to be able to add them up. So again, no cycles or round trips. You don't see the number 5 in there back on itself. Alright, so go look at the code. We're just going to do this with two classes. We basically have them kind of the main sequential class here, adjacency list task. Again, we're using a linked hash map because that will preserve the order. The order of the task is given in the flat file. So that's how I handle the order, by using this data structure. Okay, we've got add edge, source, destination, task. Get tuple just means you give it a vertex number, it turns you back everything related to that vertex, edges and tasks. Task unit means, are we going to sleep for 50 seconds? Are we going to sum 5 numbers? What is the unit of work to be done? And then get task name, of course, is sleep or sum. And here's the math function, get sum of vertices. You feed it X number of numbers to add up, and it returns you back the sum. Nothing too complicated there. Get number of vertices, goes through the flat file, figures out how many we have. We have 10. So yeah, I'll just get rid of this, sorry. Don't need that. We're just checking, then we finally build the graph, and we're just checking for cycles, right? The destination cannot equal the source, so. Okay, so we see the flat file here. Again, first column vertices, second column edges, third column is the work description and unit. And we run it, right, and we see, okay, vertex 0. Again, if it has nothing more than 0, it means it has no edges, so vertex 1 obviously has 0 here, it means 0 edges. Vertex 2 now is a sum function, so it's going to sum the previous two vertices, namely 0 and 1, summing two numbers, 0 plus 1 equals 1. Vertex 3, again, the description goes for each edge, 0 sum 3, 1 sum 3, 2 sum 3 numbers, and then you get sleep, sleep, sleep. Okay, cumulative sum of vertices is 45. Yeah, looks good. There it is. And now we get down to the operation where we're going to do sequential and parallel stuff together. Threads, I have 8 cores, so I'm just assuming 10 threads, roughly the same number of cores. So we did everything sequentially, there we go. And then the interesting part is down here where we kick off, we redo everything with blended sequential and parallel. So we're going basically from 0 to 9 vertices. We get the work description in the unit. If it's sleep, the main thread will sleep, capital T thread. If it's 2 or 3 as predefined by us, you know, B to C, C to D, and it's a summing operation, well that kicks off the parallelism. So that's that OR operation there. So if thread is 2 or 3, now we're going to call to the parallel class. Okay, which is similar to the main class. It's just we're using runnable here to allow it to kick off multiple instances. Synchronized static, getters and setters, yeah. So we can just get the local sum with that local thread. Okay, so of course we join for these parallel threads so we get the right sum back. Here's the getter. Basically, the parallel sum of vertices and the sequential should kind of equal each other, and you know, indeed they do, right? There's parallel, right? And they take about the same amount of time. Again, this is a tiny program, so the overhead for the computer to manage the threads and the cooks in the kitchen probably doesn't. Parallelism doesn't really outweigh the benefits. Don't outweigh the consequences here. So sequential is probably a little faster. So, and we're just keeping track of the heap or memory. Again, very little. Okay, so just 2 classes here, parallel, and then here's kind of the sequential, or the main thing that's basically sequential. Again, this, these 2 classes are related. It's just this one is a parallel version. Okay, so that's going to do it. Project is on track. I'll have that by tomorrow morning, Monday, and then I just need a few more days to finish the redo of homework 2, and I'll get that to you and put out a Trello card. Okay, so I appreciate your patience. I think I'm almost caught up. I'll see you later.